SATA. The Serial Advanced Technology Attachment. Solid-state drive, commonly referred to as SATA, utilizes the SATA 3 interface, which offers a theoretical maximum bandwidth of 6 gigabits per second. This translates to approximately 550 megabytes per second for real-world sequential read speeds and about 500 megabytes per second for write speeds. The random access latency typically falls below 0.1 milliseconds, in contrast to the 10 to 15 milliseconds found in standard hard drives. Consequently, a SATA SSD can feel over 100 times more responsive than a hard drive, despite the actual speed difference being only around 5 to 6 times. Interestingly, most SATA SSDs are often limited by the interface rather than the flash memory itself. It's akin to having a race car hindered by a tractor, resulting in a performance bottleneck. mSATA. The mini SATA solid-state drive, or mSATA, employs the same SATA protocol as standard SATA SSDs, but comes in a more compact circuit board format. Performance generally ranges from 450 to 550 megabytes per second, making them nearly indistinguishable from 2.5-inch SATA drives in terms of speed. The primary distinction lies in their size rather than their performance. In many older Ultrabooks, an mSATA SSD took up less than a quarter of the physical space of a traditional 2.5-inch drive while providing equivalent performance. M.2 SATA. This SSD variant utilizes the M.2 form factor but still operates through the SATA interface. Consequently, performance is limited to around 550 megabytes per second, despite its modern design. Many users mistakenly believe that all M.2 drives are exceptionally fast due to their similar appearance, but an M.2 SATA SSD can be over 10 times slower than a high-end M.2 NVMe SSD. The shape has evolved, but the speed limitation remains unchanged. NVMe Non-Volatile Memory Express Solid-State Drive, commonly referred to as NVMe SSDs, connect directly via PCIe lanes instead of the traditional SATA controller. NVMe can handle up to 65,535 command queues, each capable of managing 65,535 commands, while SATA is limited to a single queue with just 32 commands. This significant boost in parallel processing greatly minimizes bottlenecks. Consequently, it leads to reduced latency, increased input-output operations per second, and significantly enhanced performance during demanding tasks. To put it simply, SATA functions like a narrow local road, whereas NVMe operates like a wide multi-lane expressway. M.2 NVMe M.2 NVMe Non-Volatile Memory Express Solid-State Drive, or M.2 NVMe SSDs, merge the sleek M.2 form factor with the NVMe protocol. Depending on the PCIe generation, speeds can vary from 1,500 megabytes per second to over 14,000 megabytes per second. When compared to a SATA SSD, an M.2 NVMe drive can deliver sequential throughput that is 3 to 25 times greater. A contemporary operating system may boot in 10 seconds on SATA, but substantial professional workloads often demonstrate even more significant improvements beyond just boot times. PCIe Gen 3 Peripheral Component Interconnect Express Generation 3 Solid-State Drive, known as PCIe Gen 3, generally utilizes 4 PCIe lanes, offering a maximum bandwidth of around 4 gigabytes per second. Most high-end drives reach sequential read speeds between 3,000 and 3,500 megabytes per second, with random performance surpassing 500,000 input-output operations per second. In comparison to SATA SSDs, Gen 3 drives are approximately 6 times faster in sequential tasks. Even now, Gen 3 is more than adequate for gaming, software development, and everyday productivity. PCIe Gen 4. This version doubles the per-lane bandwidth compared to Gen 3. High-end Gen 4 SSDs typically achieve read speeds between 7,000 and 7,500 megabytes per second, along with over 1 million input-output operations per second. When transferring large files, speeds can be nearly double that of Gen 3. However, for many routine tasks, the improvements are less pronounced, as software often becomes the limiting factor before storage does. This discrepancy is why benchmark results can appear significantly different, while real-world performance differences may seem modest. PCIe Gen 5. Once again, bandwidth is doubled. Top-tier Gen 5 SSDs often surpass 14,000 megabytes per second for reads and 12,000 megabytes per second for writes, achieving over 2 million input-output operations per second. This performance is about 25 times greater than that of a SATA SSD. The trade-off, however, is increased power consumption and heat output. Some Gen 5 drives can draw more than 10 watts under load, prompting manufacturers to use larger heat sinks. Consequently, your SSD may require cooling solutions typically reserved for processors. DRAM SSDs with DRAM include a dedicated dynamic random access memory cache, which usually ranges from 512 megabytes to 4 gigabytes based on the drive's capacity. This DRAM holds the flash translation layer, enabling the controller to access data more quickly. Under continuous workloads, DRAM-equipped SSDs often sustain near maximum speeds, while those without DRAM may face significant slowdowns. In professional scenarios involving large video files or virtual machines, the performance gap can be considerable. DRAM-less dynamic random access memory. Less solid-state drive, or DRAM-less SSD, forgoes dedicated DRAM cache to cut costs. Many contemporary models utilize host memory buffer technology, which taps into a small portion of the system's RAM instead. For lighter workloads, performance can be surprisingly similar to that of DRAM-equipped drives. However, during extensive sustained writes, speeds may plummet from several gigabytes per second to just a few hundred megabytes per second once the cache is depleted. Imagine it as a sprinter who starts off strong but tires out quickly. QLC Quad Level Cell Solid-State Drive, commonly referred to as QLC NAND, is capable of storing 4 bits in each memory cell, which enhances storage density and lowers the cost per gigabyte. The typical endurance ratings range from 100 to 300 terabytes written for every terabyte of capacity. However, write speeds can significantly decrease once the SLC cache is filled, occasionally dropping below 200 megabytes per second on some budget models. Nevertheless, QLC allows for the production of affordable 4 terabytes and 8 terabytes consumer SSDs. More storage at a lower price but with reduced endurance. TLC, Triple-Level Cell, Solid-State Drive, or TLC NAND, stores 3 bits per memory cell and is considered the optimal choice in contemporary SSD design. Endurance ratings typically range from 600 to 1,200 terabytes, written for a 1 terabyte drive, often surpassing those of comparable QLC models by several times. TLC also offers better write performance under continuous loads. This combination of endurance, speed, and cost is why nearly all premium consumer SSDs utilize TLC NAND. MLC Multi-Level Cell Solid-State Drive, known as MLC NAND, stores 2 bits per memory cell. Historically, endurance ratings for high-capacity models often exceeded 3,000 terabytes written. In comparison to TLC, MLC offers greater durability and improved sustained performance, albeit at significantly higher manufacturing costs. Many enterprise SSDs employed MLC technology before newer advancements made alternative options viable. SLC, Single-Level Cell, Solid-State Drive, referred to as SLC NAND, stores a single bit per memory cell, making it the fastest and most robust flash memory architecture available. Write endurance can surpass 100,000 program erase cycles, in contrast to approximately 1,000 to 3,000 cycles for TLC NAND. Additionally, read and write latencies are lower, since the controller only needs to differentiate between 2 voltage states instead of multiple levels. The trade-off, however, is in storage density, as an SLC SSD can be several times more expensive than a TLC SSD of equivalent capacity. U.2. These SSDs usually connect via PCIe x 4 interfaces and commonly utilize enterprise-level controllers along with NAND flash memory. Their capacities often span from 4 terabytes to more than 60 terabytes. In contrast to the majority of consumer SSDs, U.2 drives allow for hot swapping, feature advanced power loss protection, and have endurance ratings quantified in drive writes per day. While a consumer SSD may be intended for sporadic heavy usage, a U.2 enterprise drive is engineered for continuous operation 24/7.